I'm not coming in. Hello, and welcome to the lecture series on uncertainty. This is part one of the uncertainty lectures. We'll give some definitions, introduce some concepts, and immediately jump into our first method for dealing with uncertainty, which is scenario analysis. From that, we'll proceed to the next logical method, that's expected value analysis. And last, we'll have an example with sensitivity analysis. Let's provide some definitions. Uncertainty is the lack of knowledge about the relative chances or probabilities of events that may or may not occur. Notice the word lack of knowledge. You don't know what's going to happen. Risk, on the other hand, is a quantifiable measure of the chances or probabilities, particularly of undesirable outcomes. Sometimes it's a function of the chance or probability. The major difference between these two definitions is that with the situation of risk, we have a quantifiable measure, or we're willing to assume a quantifiable measure of the chance or chances of the uncertain outcomes. With uncertainty, we know they're uncertain, but we either don't have numbers or we're not willing to assign numerical values to the probabilities. Well, let's proceed to scenario analysis. This is the easiest way for dealing with uncertainty. Basically, what you do here is you formulate several outcomes that may or may not occur, and then you simply perform the analysis. And what's nice about scenario analysis is that you can use any criterion with it. Our popular criteria such as future worth, present worth, annual worth, and even our difficult ones, rate of return and benefit cost ratios. So let's proceed into our example. Let's say we have a project that has an investment of $200,000 and it has an annual net cash inflow that is going to generate $70,000 for a period of 8 years. And we'll call this the most likely outlook, the most likely scenario. On the other hand, if the economic situation is poor, then we would have a pessimistic outlook, and perhaps the lifetime would drop from 8 to 7 years, and the annual inflow would only be $50,000. We might have a very good economy, and then we could have an optimistic outlook. Inflow would be $85,000 for a longer lifetime, specifically 9 years. So here's a review of the numbers for our example. The pessimistic scenario has a lifetime of 7 years, inflows of $50,000 per year, most likely 8 years, $70,000 per year coming in. And last, the optimistic outlook, 9 years with an inflow of $85,000 per year. So we can go ahead and use a minimum attractive rate of return of 20%, compute the present worth for each one of these scenarios. Here we're computing the present worth of the cash inflows. For the pessimistic scenario, that's $50,000 per year, lifetime of 7 years, so the series present worth factor is based on n equals 7. That gives us a present worth of the inflows of $180,230. Do the same thing for the most likely and optimistic. What's changing here are the annual inflow values and the lifetimes. 8 years for most likely, 9 years for optimistic. So then we have the present worth of the cash inflows for each of the 3 scenarios. And then, of course, we would simply subtract the present worth of the investment. That's $200,000 in each case. So we get minus $19,770 for the pessimistic scenario, $68,601 for the most likely. That's the $268,601. That's our positive contribution, the inflows, minus $200,000 investment. And for the optimistic scenario, $342,632 minus $200,000. So we have our 3 numerical values of present worth. And then if we're comfortable with simply looking at each of these 3 values, then we can go ahead and try to make a decision based on that. Well, let's extend this example, use the same numbers, but add some more information. Let's say we're willing to assign probability values to the 3 outcomes, specifically 20% probability to the pessimistic, 50% to the most likely, and 30% to the optimistic outcome. Note that the probability values have to add up to 1, as they must. Then we can simply compute an expected present worth. We take the 20% chance, apply it to the negative 19,770 present worth for the pessimistic scenario. 50% is applied to the most likely present worth of 68,601, and 30% to the optimistic present worth. And then that gives us an expected present worth of 73,136. Based on that, it would appear to be a favorable project. The expected value analysis is a reasonable approach if the firm can tolerate the risks of losses. If it's a large firm, large manufacturing or distribution firm, then typically it could tolerate the loss for that pessimistic outcome of minus 20,000 approximately, provided that, in the long run, most of the projects are going to generate positive expected present worths. So that expected value analysis, it works with present worth if you know the revenues, of course. It works with future worth and annual worth if the lifetimes are the same. However, it doesn't work very well with rate of return or benefit cost ratio. Those are relative measures. You need to have a more sophisticated methodology for dealing with that if you wanted to get an expected rate of return or benefit cost ratio. Typically, you'd have to resort to some type of simulation analysis for these two criteria. Let's go to a different example now and show sensitivity analysis. Let's consider an employer who requires his employees to drive a car. So there are two options. The employer can buy a car and pay all the costs, or the employer can reimburse the employees, let's say 30 cents a mile, for the business use of their private cars. Let's look at some typical data for this type of decision. Let's imagine the cost of the car is $25,000, that it would be kept for 5 years if the employer buys it, and then it would have a resale value of $5,000. The insurance cost might be $1,200 per year, license and taxes per year may be $400. Well, we need more data. Let's say repair costs are $800 per year. Fuel costs 5 cents per mile. Oil, maybe every 5,000 miles we need an oil change. That's going to cost maybe $25. And every 40,000 miles we'd have to change the tires. Let's allow $600 for a new set of tires. So if the minimum tractor rate of return is 12%, then the question is, under what circumstances should the employer buy a car for the employee or the employees? The approach here is to separate the costs into fixed costs that do not depend upon the miles driven for business use and variable costs that do. Let's go ahead and do that. Let's take the loss in value. This car is going to drop in value from $25,000 to $5,000 over 5 years. So let's convert that to an annual loss in value using our 12%. So capital recovery factor applied to 25, sinking fund factor applied to the 5,000 with the opposite sign. That gives us an annualized loss in value of $6,148 per year with a 12% MARR. Now granted, the resale value of the car would depend upon the number of miles driven. But for most practical situations, let's say this value isn't going to change too much based on a typical number of miles driven for the car. Other fixed costs are the $1,200, the $400, and $800. That's insurance, taxes, and repairs. That's $2,400 a year. So the total fixed costs then would be about $8,548 per year. And that would depend very little on the number of miles driven. So we might assume that it doesn't depend upon the miles driven. The variable costs, on the other hand, do. Fuel certainly does. Oil certainly does if we follow the schedule for oil changes. And tires will do. So the total variable costs per mile then are 7 cents. The biggest component of that is the fuel cost, 5 cents per mile. Oil about half a penny per mile. And tires 1.5 pennies per mile. Now, we can formulate an equation to find the break-even point. Let the unknown variable be the number of miles driven for business use by the employees. So we set up the equation. This is our fixed cost. That's the loss in value, insurance, taxes, and repairs. And variable cost, that's the fuel, oil, and tires. That's 7 cents per mile. And we set that equal to what the employer would pay the employees for the use of their private cars for business use. That would be 30 cents. So we find the unknown number of miles per year that makes this an equality. This is called the break-even point. And in this example, it's 37,000 miles per year, 37,165. That means if the employer expects the employees to drive more than this number of miles per year, it would be better for the employer to go ahead and buy the car, pay all the costs. Otherwise, let the employees drive their own cars and be reimbursed 30 cents a mile. So here we have a graphical representation. Depending upon the number of miles driven for business use by the employee, that would be the cost to the employer. That's this line that has the intercept at the 0, 0 point. If the employer buys the car, the business owns the vehicle, then of course we have this fixed cost starting here, and it's moving out like that. So the intersection point here, close to 37,000 miles per year, is the break-even point for this example. So if the employee or employees together can share a car and together drive more than 37,000 miles per year for business use, the employer would be better off. Otherwise, the employer should simply reimburse the employees, granted that the employees are willing to do that. So let's summarize this lecture. We had some definitions. We talked about the difference between uncertainty and risk. Uncertainty is where you have a lack of knowledge. You're not willing to assign numerical values to the probabilities. Risk, you know things are uncertain, but you're willing to assign numerical probabilities to the uncertain outcomes. We presented the easy way to deal with some of these situations. That's scenario analysis. Typically, you might conduct 3 scenarios. If you get a very elaborate example, perhaps you might have 5 or even 7 or 8 scenarios. The next step up from that is expected present worth analysis. And last, we had an example with sensitivity analysis where one parameter was the uncertain parameter, and we performed break-even analysis to solve that example.